Today we're going to get started on diffusion models. Today as well, I consulted with ChatGPT and restructured the class materials. Normally, I would start straight from log likelihood and derive the equation, but ChatGPT recommended that I take the alternative approach, where I give you the overall algorithm and intuition first, and then try to derive it straight from the log likelihood. And normally I would start by introducing score matching and stochastic differential equations and blah blah blah. But I got rid of everything and moved it to the second lecture. So today, you don't need to know anything about stochastic differential equations. Everything's going to be derived using variational inference. Okay, so I think many of you have already heard about diffusion models. Am I being recorded? Okay, thanks. So how many of you have heard about diffusion models? Okay, a lot. So yeah, these days, pretty much, I think, all image generation models use diffusion as the backbone model. So what's under the hood? So last time we talked about autoregressive generative models like pixel RNN, CNN, and generative adversarial networks. And today, we'll introduce you to diffusion models. So what's the big picture? The main idea is you want to introduce, during training, you want to add noise to your image data, and you want to learn to predict and remove the noise. So you start off from your clean data X. You introduce a small noise. So this is X0 plus some noise. And this is X2, which is X1 with some noise added in, and etc. And if you repeat this step where you apply noising to the image, at the end of the day, X capital T is going to be complete noise. All the signal related to the image will be lost, and this is going to be, say, something like a pure IID Gaussian. Okay? And what you want to learn is to reverse this noising process called denoising. So you introduce a noising model, and you are going to ask your network to sequentially denoise these added noise, so that during inference or sampling, you can start from IID noise, IID, for example, STD normal, and apply these networks to denoise one step at a time until you arrive at a clean data. That's the basic idea. So can anyone really tell me what's fundamentally different about this process compared to VAEs or GANs? Let's set aside all the mathematical details. Just intuitively, what would make it work better compared to VAEs and GANs? Let's think about the inference procedure. Inference procedure, you start IID normal, pass it through some network, you get a one-step denoised image, pass it through a network again, get one-step cleaned up image, and etc. What's fundamentally different about this process? That's a good observation. So one difference is during inference, GANs and VAEs start from some d-dimensional random vector, but here we're starting from IID noise, which is of the same size as the image. That's one difference. Anything else? So our network takes image in and outputs image out. That's the student's answer. That's a good observation. Anything else? Yes? Can you speak up? Why would it be good?
So that it can remove the noise as much as we want.
Right. So the second answer is we're repeatedly applying this network over and over again until we're satisfied. So let's compare this to VAs and GANs, where you take this guy, pass it through the network, get one-shot generation of image. So here, you have a single call to the model during inference, which is good and bad. It's good because it's fast. You can generate image in one shot, in 1-4 pass. But you might not be satisfied with the quality. But here, you can repeatedly apply 4 pass as much as you want and get really cleaned up high resolution image. So the fundamental difference during inference is you're going to do thousands of iterations with the same model. So people are thinking, okay, so this is aside from today's lecture. So these days, the research community is thinking, okay, maybe it's good to do many rounds of forward inference, especially for reasoning, for complex reasoning. People are like that too. So if I ask, I don't know, the student to, I don't know, multiply 172.59 with 1,257,000, it's going to take some time for him to generate an answer, right? But versus if I ask him to give me, I don't know, 10 plus 2, then he will rather quickly generate an answer, right? So you need some. So it seems like you need to repeatedly apply the forward inference, or give a model some time to think about it, essentially. Yes, it's going to be slow, but for these kind of complicated tasks, maybe it's worth to run lots of forward iterations, forward passes. Okay, so two fundamentally different things. Here, this is image size, random image input, and output is image size. 2, you do repeated forward pass. I guess number 3 is different equation. Yes, all 3 are different, but I think this is especially important. It might be too difficult to one-shot generate this complicated looking image. Okay, so we're gonna introduce some modeling choices. So this Q distribution is, just to remind ourselves what the notation. Look at the subscript here. 0 is reserved for the clean image. And as the index increases, you get closer to IID pure noise. Okay, so if the index is smaller, you are closer to the clean data. If the index is larger, you're closer to the random noise. So compare these two. Condition on one-step cleaned up image, one-step noised image. So this process defines the noising process. How we're going to add a noise one step. So this is one step noising. Distribution on the random variable for one-step noised image is Gaussian distributed with the corresponding mean and variance. Beta t is some small number, and what you're doing is you're shrinking the mean towards 0 by multiplying square root of 1 minus beta t. So this is mean shrinkage, and you're adding some beta t amount of standard deviation noise. Okay, so you shrink the mean towards the mean and apply some Gaussian noise. That's going to be our noising process. And some notations for us to define. Alpha t is 1 minus beta t. And alpha t bar is multiplying all the previous alphas. Just some notation. Okay, so this is just rewriting using the notations above, using alphas. So interpretation is we're going to slightly shrink the signal towards 0 and add Gaussian noise. That's our noising process. Here, notice there's no parameters here. And we're going to use the neural network to mimic this distribution, or essentially undo this distribution. So in terms of diagram, you start off from clean data here, and you sample x1 according to this Q distribution, one-step noising distribution, and you repeat this process for predefined capital T number of steps. This is usually on the order of 1,000 to 2,000. So if you ask image generation model to generate images, it's typically going to be thousands of iterations. It's why that's so slow compared to generating text. So if you repeat this step many times, at the end of the day, you're going to observe something that's almost IID Gaussian. Okay, so this notation here means just a shorthand. If in case you never seen this, x1 random variable x1 during xt conditioned on x0. It's just a shorthand notation. So the distribution of all the axes given the clean image x0, that's multiplying all the Q distributions by chain rule. And like I said, the for process has no learnable parameter. This is our design choice. So we can express this in closed form. So a very useful property is if we condition on the clean image, distribution on random variable xt, meaning t-step noised image, is Gaussian distributed with square root of alpha t bar of x0 and 1 minus alpha t bar of standard deviation. So if you already have clean image, you don't have to repeatedly sample t steps of Gaussian. You can straight jump to anywhere you like using this formula. This is just a property of Gaussian distribution. So how do you sample t-step noisy data? You can do it efficiently. Given the clean data, you just you shrink the mean by one-shot multiplying square root of alpha t bar. Remember, alpha t bar is multiplication of all the previous alphas, and square root of 1 minus alpha t bar times epsilon, where epsilon is a standard normal distribution sample. It's easy to prove this yourself if you want to see whether this is true. And so, at least for noising steps, you don't need to simulate all the previous noising steps. You can just jump to anywhere you like, as long as you have the clean image. This is what makes the training very efficient. And so during training, you just choose a random t, and corresponding amount of noise can be computed exactly with this formula. Okay, so the intuition is you start from clean image x0, you apply t steps of noising, and when t is small, as you can see, alpha t bar, like I said, is defined as multiplication of all the previous alphas. It's going to be close to 1. So it's not, the mean is not going to be shrunken that much, and correspondingly xt is going to be close to the original clean image. So image is very slightly noisier when t is small. When t is large, alpha t bar is going to be very large because we're going to keep multiplying something less than 1. So mean is going to be shrunken to 0, and xt is going to be almost pure noise. So as we progress through noising steps, we start from clean image to all the way to pure noise. So how about the reversing step? So this is the complicated part. How do we train a model to reverse this noising process? That's the key step. Because if we can do this, we can start from IID normal sample and repeatedly feedback its output as input and repeatedly call this denoising process until we get a satisfying clean image. So that's what we want to learn. Starting from pure noise, we want to train a model that can continuously denoise the input image and use its own output to noise again and again and again. So we're going to model it as a Markov chain. So notice the data here, that's the neural network parameter. P theta of x0 all the way to capital T. That's going to be by probability factorization by chain rule. P of xt. Remember, in chain rule, you're supposed to write it as product of P of xi given x predecessor of I, and xt doesn't have any parent, right? Here, there's no arrow incoming, so xt is on its own, and all the other guys is xt minus 1 given xt. Okay, so that's the joint distribution. And each reverse step, we're going to model it as Gaussian distribution. So reverse step means this is one step cleaned up image. So given xt, one step distribution on one step cleaned image is Gaussian distributed. Because we're going to model it that way, with mean parameter and covariance parameter outputted from the model. So model is going to take as input xt and step index t and output the mean parameter for a one-step cleaned up image and correspondingly for the variance as well. Okay? So compared to VAEs, the mean model now also takes as input these natural number, the time index. So the big idea is we want to learn how to denoise one step, because if we can do this, we can repeatedly call this model many, many times. So yeah, xt going to xt minus 1 is one step denoising, and the reverse, going from xt minus 1 to xt, is noising. Noising is done through our modeling choice here on following this distribution here, mean shrinkage and adding Gaussian noise. All right, so I already explained it. So going left to right in this figure follows a fixed Q distribution without any parameters. Reverse process, we're going to follow the Gaussian distribution where the mean parameter and the variance parameter is predicted by the network. So for process easy, it's fixed, just shrinks noise, shrinks mean, adds Gaussian noise. Reverse process, we have to learn it. It's hard, and this is the key step in diffusion models. Okay, so we had the closed form expression for generating t-step noised image given the clean image, and the model should receive xt and t and should generate the added noise. So we're going to see different parameterizations. Well, this is just one specific realization where you parameterize the model so that it takes as input t-step noised image, step index, and outputs the added noise that's added to xt to generate xt minus 1. So if you know the noise that's added, this component here, if you know this, then you can estimate the clean image by solving for x0 here, right? So we already had the expression relating x0 noise and t-step noised image. So if we knew the noise given x0 and the predicted noise, we could just use the formula to generate predicted clean image. So noise prediction is actually denoising because xt and x0 is related with this formula. So there are many parameterizations. They are all pretty much the same. So you could train a neural network that predicts the added noise, or you could train a network to directly predict the clean image, or you could train a model to predict the velocity style combination, indicating how much the rate of change of added noise or something like this. If you want to view this multi-step as a continuous time, you could do something like that. But it's pretty much all the same because everything's related with this formula. So if you know one thing, you know the other through this relation. And depending on the application, you might have different results. It might be easier to predict the noise, or it might be easier to directly predict the clean image. It all depends on your task. So in today's lecture, we're going to focus on the original DDPM style noise prediction. DDPM is the underlying paper that started all this. And we're going to train a model to predict the noise. Okay, so how do we train this? So sampling the clean data, that's just sampling an image from your training set. And you need to sample the index t from predefined t, capital T. This is on the order of a couple thousands. And epsilon, that's just standard normal noise. And starting from clean image, you use the formula here for the noising steps to generate t-step noised image xt. And then you're going to train a model, epsilon model, so that this is the regression target. This is your prediction, which takes as input xt, the t-step noised image, sampled noising step index, and minimize the MSE. So during training, we don't follow 2,000 steps. We just pick a random point in time, one-shot generate t-step noised image, and then plug it into the network to predict the noise. Because during training, we don't have to follow these diffusion steps because we can directly one-shot generate t-step noise. So network learns to predict the noise that was added to the clean image. That's the training procedure. So here's the algorithm. So first, you sample clean data from your dataset. You sample a random time step from 1 through capital T. You sample IID noise. And you one-shot generate t-step noised image by using the equation here. One-shot generate t-step noised image. And you generate a prediction by plugging this into your network. And you minimize the MSE between the actual noise and the predicted noise. And you update your parameters. Okay. So how about sampling? So sampling is a little bit complicated. Not so much. So now we need to model each reverse step as Gaussian. So remember, this was our modeling choice. So p theta of x, p theta of xt minus 1, one step cleaned up image given xt. We're going to model it as a Gaussian distribution where the mean and the variance parameters are predicted by the network. Here, let's simplify a little bit. And for the variance, let's just use a fixed variance and just predict the mean parameter given xt and time step t. So sigma t is predetermined noise schedule that depends on time index. And if we sample, if we want to sample Gaussian with this mean and variance parameter, we can generate the sample this way, right? So a sample xt minus 1 under this Gaussian model is the mean plus IID sample plus standard deviation. This is how you sample from Gaussian distribution, right? So the for process has a useful posterior distribution. So let's go back. The for process. So for process, which is one step noising, is Gaussian distributed with square root of alpha t, xt minus 1, 1 minus alpha t, variance parameter. So let's think about this posterior distribution. So here, now compare the indices. Compared to before, the indices has been flipped. So the Lewisian distribution is xt given xt minus 1. We're interested in finding out the reverse, q of xt minus 1 given xt, and also given the clean image x0. So the reverse process, sorry, the forward process, the posterior of the forward process is also Gaussian distributed, where the mean follows this equation here. So it looks a little bit complicated, but you can derive it yourself. I don't know if I have the derivation somewhere. I think I have something similar later. Yes. Anyways, you can derive it yourself. So posterior is also Gaussian distributed with the following mean parameter. Bunch of coefficients multiplied times clean image x0, bunch of other coefficients times xt. So what's the interpretation? If we knew the clean image x0 and the best reverse mean from xt to xt minus 1 is known in closed form. So once again, if we knew, if we're given x0, the mean going from xt to xt minus 1 is given in closed form. But the problem is, during inference, we don't know the true x0. So this equation is relating x0, xt with respect to xt minus 1. So we're interested in the mean or expected value of one-step denoised image given xt and clean image. So this relationship relates clean image, t-step noise image with the predicted mean of xt minus 1, one-step denoised image. And that's related through this formula just by the definition of our noising step Q. But the problem is we don't know this guy during inference. So during sampling, we only have access to xt and the model prediction for the noise. So from the forward noising equation, where we generate t-step noise image one shot, we can estimate the clean image as following. So here, solve for x0. And here, epsilon is going to be predicted by our trained model. So here, let's solve for x0. So x0 hat, or estimate of the clean image, through the relationships that define t-step noise image. That's going to be just solving this equation here with respect to x0. So it looks like this we know, this we know, this we know. So if we plug in xt and t to our trained model to predict the one-step noise, we can solve for x0 hat. So using our trained model, we can now estimate x0. So we can now define the reverse mean by plugging this estimate into the posterior mean. So here, we're going to plug in here our estimate, x0 hat, derived from epsilon theta and xt. and t. Okay, so this we had this relation, but we didn't know x0. But we're going to use a model to predict epsilon, and use the four noising step equation to generate an estimate of x0. We're going to plug it into the posterior mean. So now we're going to plug in the place of x0, x0 hat. And if you just plug this in here and simplify, the equation looks like this. After simplification, the predicted mean of one-step denoising is 1 over square root of t, xt minus some constant times the model output. Is this obvious? It took me, I don't know, maybe 2 lines. So you plug in here, expression here, and simplify, you can arrive it here. Here you need to use the relation between alpha t bar and beta to simplify. Okay, now looks good. So one-step denoising, predicted mean of the one-step denoised image. We can now compute it, right? We have xt and t. We have the trained network. Now we can predict the predicted mean of one-step denoised image xt minus 1. All right, so going back, if we had the predicted mean of one-step denoising, we can sample IID, Gaussian, apply the standard deviation that's pre-scheduled. That's going to generate a sample from this Gaussian distribution. So this allows us to sample xt minus 1, given xt, x0, and trained network epsilon. Okay? So that's this line here. Sampling from p theta of xt minus 1, given xt. Here. Okay, so so combining these two equations, this guy is what we derived here. Combining these two, just writing everything in one line of equation. Sample, one-step denoise sample. So one step sample xt minus 1. We can directly generate the sample given xt, trained network, xt and t, and this guy adding noise. So now it seems like we have an algorithm. We can start from IID standard normal distribution, and given this formula, we can now generate one-step denoise sample. Right? Given the one-step denoise sample, we can repeat this process for, I don't know, 2,000 iterations, generate a clean image. So we already have an algorithm. Okay. So yeah, it's the algorithm slide. This is how you sample. First, you sample pure noise. Then, for a couple thousand iterations, 2,000 iterations, I'll explain this part later. We sample the Z here. That's just a standard normal sample. And we invoke the model with our xt and t. This is going to be the predicted noise. And one-step denoised image is going to be generated using this formula. So here, this is just to, so if you look at this equation, here we have where the magic happens. That's this component here. That's actually one step denoising. That's where most of the magic happens. Here, we're just adding noise. Magic cleaning, adding noise. But if you think about it, at the very last iteration, you don't want anything blurry, right? You don't want to do this at the very, very last iteration, because you want as clean image as possible. So this line here is just to prevent that. If t is 0, you don't want to add the noise. You just want the magic part. For all the other t's, we're going to follow the equation as is, verbatim. But at the very, very last iteration, we're not going to inject the noise, because this is going to make the image look less clean. Okay, so we talked about both the training and sampling procedure. So training, you choose some random time step, use the magic one step in one step you generate t step noised image using the formula, this formula here, and you train the network to predict the added noise. And it's fully parallelizable over data. You don't need thousands of iterations. For sampling, you actually need to invoke the model thousands of times to generate a single image. You start from pure noise. You use the formula here to repeatedly add noise, clean the image, repeat this process thousands of steps, and you're going to get cleaner and cleaner image per every iteration. And unlike GANs, diffusion models are very stable to train and produce very, very high quality samples. This is the backbone model for pretty much all the modern image generation tools out there. But like you already have experienced, sampling can be painfully slow because you need to do thousands of forward pass. So how about the architecture? We haven't talked about this yet. So okay, so model is the noise prediction model, and the inputs are t-step noise image and time step. So the common architecture is a unit backbone. So we haven't really talked about units in the class, right? This used to be in previous years, but it looks something like this. So it's image in, image out architecture. So it's basically a convnet where you take an image in. I'll draw the activations, which is 3 channels, right? And you keep shrinking the image, but compensate for that by using more channels. So this is conv1, conv n. This is the convolution part. And you have the deconvolution part using striated convolutions that we talked about. Now you do the reverse process where you use less channels. And get an image out. And per each corresponding conv layer and deconv layer, you have residual connections. That's the unit architecture that's used a lot in image generation. And just one additional tweak you need to do is make sure you can take as input the natural number, which is time index. Also, you need to change the unit so that you can better encode this timestamp information. So compared to the dimensions of the image, timestamp t is just single dimension. So how do you inject this noise, inject this information more naturally? And the typical choice is to use what's called time embedding. So this is similar to positional embeddings that we talked about in LLMs. Here you use time index to generate an embedding into your network. Because if you just provide a single number compared to this guy who's like, I don't know, 1024 times 3, that's just a single number. This number is going to get buried during Makeshift multiply. So we're going to take this number and generate an embedding vector, so you can have a significant portion in terms of the proportions of the dimensions that enter the network. So we're going to use sines and cosines and generate some embedding that's a function of the time index. And that's pretty much the change you need to apply to the unit to make it work for multi-step denoising. And the original DDPM paper used 1,000 steps with this kind of scheduling. With beta 1, beta t, you have smooth scheduling between indices. And this was the generated quality. Compare this to the VAE generated faces and digits. So the sheer difference in resolution was revolutionary when it came out. And I think yes, mathematical details are important, but the critical thing is give chance for the network to repeatedly clean the noise by using thousands of iterations on itself. So you can do a lot of interesting interpolation in the latent space, but I'm going to skip the details. Okay, so normally I would just start from here. This is my go-to flow from last year, but ChatGPT recommended I reverse the explanation. Do you guys like it? I give you an intuition and algorithm first. All right, so anyhow, this is okay. We guided the training loss and inference procedure from the intuition, but we're interested in finding out where all these equations come from. So, as always, we're going to start from the likelihood, and here, similar to VAEs, we're going to derive variational lower bound. So I think there are a couple of places where I skipped the derivation a little bit, but it's not difficult, and I'm sure you guys can prove yourself. But most of the important steps are in the slides. So we observe a clean data x0, but we're going to introduce a noisy trajectory of latent variables. So x1, x2, all the way to xt, are the latent variables. These are random variables. And we're interested in the marginal likelihood. So under the model, we want the probability assigned to x0 as high as possible. What is the probability of x0? So here, you need to form the joint distribution of all the random variables and marginalize out or integrate out all the nuisance variables, x1 through xt. And we're going to stick to the fixed for process. Here, we already defined the noising steps earlier. We're going to use that. So here, I'm just going to, do the same thing. Divide and multiply by the same distribution, which is our for process. And we're going to turn this intractable marginal likelihood into a tractable training objective. So, as usual, I'm going to express this integral and distribution as expectation of the random variables x1 through xt, sampled from, or not sample, that follow this Q distribution, Q of x1 through t given x0. So I'm going to rewrite this integral as expectation under Q distribution of the ratio between the likelihood, the joint distribution and the Q distribution. And as usual, I'm going to once again apply Jensen's inequality to the negative log likelihood. So apply negative log here. And this is from Jensen's inequality. So its negative log likelihood is upper bounded by expectation of the Q distribution of negative log ratio of the joint and the Q distribution. Now, taking expectation over data x0, I'm going to, so this is, the random variables here are x1, x2, xt, or in short, x1 through t. If I introduce additional random variable x0, now we're going to use it, we're going to write it as a random variable including x0. Okay, so the learned reverse process factorizes because it's a markup chain, xt, p of xt, p of xt minus 1 given xt. And the for process factorizes as well, as we already talked about all these, by the way. Q of xt given xt minus 1, etc. So this is clean image, one step noised image, and the order is reverse. Anyways, okay, so let's try to unpack what's inside the expectation here. That's negative log of the joint over Q distribution. So we can unpack this as following. Negative log P, a probability of pure noise, minus sum of the log probability of one step denoised image and xt, and sum of the log of xt given one step denoised image. So here we're going to massage the equation just a little bit. So using Bayes' rule and property markup chain for the for process, we have this relation Q of xt given xt minus 1 is the expression on the right hand side. Can anyone see or tell me why? So Q factorizes in this manner, and why is this true? Is this obvious? Why? At the first glance, doesn't look obvious because now we have this nasty x0. without x0, this is just pure base rule, right? Why can't I safely insert x0 here? Right, because of the Markov property of the Markov chain. If you condition on the past, all the previous random variables, if you condition it, doesn't matter. Exactly. Okay, so using this relation, I'm gonna insert the expression to here in the Q. Okay, so what's going to happen? I have a sum of index t of log Q distribution. So what's going to happen? I have the ratio between Q of xt given x0 and Q of xt minus 1 and x0. And I'm going to compute the log, sum of the log probabilities. And I have beautiful telescoping sum where everything cancels out except the terms in the beginning and the end, right? So at the end, I have Q of xt given x0. And in the beginning, I have, I guess, okay, let me look at it piece by piece. Okay, so just to make sure, this guy came here, and this guy came here, and this guy, we inserted this factorization here, and this term came here. And here we switch the index. So here we used to sum from 1. Now we're going to sum from 2. And when t is equal to 1, this guy came here. So just notice the index change. So this used to sum from 1. Now we're going to sum from 2. And when index is 1, it's here. Okay, so we can see first term doesn't have any parameters. And second term looks like it's going to be the bulk of the formula. This guy only depends on x0 and x1. So let's rewrite it in the following way. So the expected negative log likelihood is upper bounded by Jensen's inequality, sum of 3 terms. First term is KL divergence between Q of xt given x0 and PT, P of xt. But doesn't really matter because there's no parameters inside. Second term is going to be sum of all the intermediate time steps for the diffusion steps. That's actually turns out, KL divergence between Q of xt minus 1 given xt and x0 and p theta. And this is the leftover term that only relates clean image and one step noise version of the clean image. So the bulk of the magic happens inside here. So it turns out KL between these two distributions. Given the clean image, what is the posterior distribution of the denoise image? We worked this out previously. And this is our model that predicts the distribution on one-step cleaned image through the neural network. So it looks like if we unpack this, the natural flow would be to encounter MSE somewhere, right? Which was our training objective. So we modeled everything as Gaussian. So we already worked out the posterior distribution for the noising step earlier in the slides. we use the mu tilde and beta tilde notations. And this is our model, where model predicts the conditional expectation of one-step cleaned image. So if the variances are fixed, are parameter free, then KL mainly matches the means. So it's actually some constant and posterior mean and predicted mean. So if we use the noise prediction parameterization of mu theta, which relates mu theta with respect to epsilon theta we saw earlier in the slides, then this becomes some weighted version of epsilon minus epsilon theta. We had the relationship between mu theta and epsilon theta, right? So this is nothing but our training objective. Okay, so let's do a brief summary. Diffusion models learn to reverse our noising process, which is Gaussian, where we shrink the mean towards zero just a little bit per each step and add some Gaussian noise. So we can generate one step forward noise, and the training objective is predict the added noise through a neural network that takes as input T-step noise image and time index. And for sampling, we sample from standard normal distribution and then repeatedly apply the equation here. This guy, to generate sample for one-step clean image under Gaussian assumption. Okay, so and the underlying network is usually going to be UNet, where for the convolution steps, you shrink the height and width dimension, but compensate by increasing the channel dimension at each convolution layers. And there's a one-to-one correspondence between a convolution layer I and deconvolution layer J. And here you add, because the input activations dimensions are the same, you use residual connections there for each corresponding blocks of convolution and deconvolution blocks. An important thing was we needed to provide some information about the time index as well, because epsilon theta is also a function of time, but time is a single dimension compared to millions of dimensions of image. So to provide some significant context for the time, we turned it into embedding similar to the positional embedding in LLMs. Okay, so that's it for today's lecture. I think there were quite a lot of equations today, but if you just take step by step and derive and realize the connections between different things, it's not too difficult. And I think you can master this once you do your homework on diffusion models. Did the homework on VAEs and GANs come out yet? Yes, it did. Okay, and for the project, we're putting some final finishing touches. We want to make it perfect before I release. So I think it's going to be released today. Oh, it's released? Okay, good. Was it released today? Okay, very good. So take a look at the project description and if you don't know anything about SSDs, that's completely fine. You can ask ChatGPT how SSD works. It's not too important that you know all the details. And like I said, you're welcome to use AI tools, but do not just copy paste the output. You cannot just dump the output of ChatGPT, okay? You have to write it in your own language and stuff. And so there is a final exam and the project, and part of the project score, it comes from your score, your ranking on the leaderboard. So there's a leaderboard, and how you perform on the leaderboard at the final day will contribute significant portion to your project score. So it's going to be combination of the leaderboard score and combination of your score, your model score on a privately held test set that's unreleased to you. So you cannot just overfit to the leaderboard, okay? Your score is going to be combination of leaderboard score and some private unreleased data set. So if you just so there was one team last year where they just completely overfit to the leaderboard. They were ranked top 2 among 35 teams, but their score on the Helda score was very, very low. I don't know, maybe they hacked the system or they completely overfit, but it performed very, very poorly. All right, so that's it for today's lecture. Thanks.